Here is the first part of your fall semester exam review. We're going to look for, it says for each function family, give the parent function and sketch the shape of the graph. So for a linear, that means that f of x is equal to x. And there's your parent function. Absolute value, f of x equals the absolute value of x. Looks like this. Quadratic, f of x is equal to x squared. That's a parabola. Cubic, f of x equals x cubed. There's your parent function. Square root, f of x equals the square root of x. Looks like this. Cube root, f of x equals the cube root of x. Looks like this. Reciprocal, f of x equals 1 over x. Looks like this, and we have two asymptotes. One right here, and one right here. Greatest integer, you were supposed to change to signum. So signum is SGN of x equals the absolute value of x over x. And then it looks like this. All right, so then here's some explanation of all the transformation rules we should know, and then we're going to describe the transformations. Okay, so I have had lots of questions on number 1 already about, wasn't there something about 5 could be both things, this and that? And yes, okay, you have some options here when you have a reciprocal function, but only when it's a reciprocal function, not just when you have something in the denominator. The easiest way, I think, to remember this is that if you have a number in the numerator, think about factoring it out, and then it's going to be affecting the y value. If it's in the denominator, then you can say it affects x like it would here. And what I mean by factoring it out is if you're trying to figure out if this is a vertical or horizontal compression, if I rewrite this as -5 times 1 over x plus 7, and that's -2, then it looks way more like an actual vertical stretch, and then this is the only thing that's affecting your x. So these have the same value. You could force that into the denominator, but I wouldn't suggest it. So when we go to look at our transformations, so we have this negative, right, which is going to be a reflection, so we know that. Reflect, and then in which axis? Well, again, if it's something that's on the outside and it's out here, then we can say that that's affecting our y, which means that we're going to reflect in x-axis. However, for a reciprocal function and for the reciprocal function only, whether you reflect it in the x or you reflect it in the y, you're going to end up with the same thing in the end. So it doesn't really matter. Just know that this only works for the reciprocal function, and you're not doing both. It's one or the other. So that's my reflection. That 5 is going to be a vertical stretch. By a factor of 5. And then this 7 right here is going to be a transformation, or a translation rather. So I'm going to translate. That's going to be left 7 and then down 2. All right, number 2. This is a cube root function, right? I don't have anything out in the front here. So this negative is inside of this before I take the cube root. So we say that it affects the x, which means that we will reflect in the y-axis. This 2, since it's in here with the x, this is going to be a horizontal, and this will be a horizontal compression. Factor of 1/2, because x lies. And then I translate We're going to go right 1 and up 5. All right, so this is a greatest integer function, but it really doesn't matter. It doesn't matter what it is because the transformations are what we're concerned with. This is the function that's happening, whether it's a cube root, a square root, a quadratic, an absolute value, whatever. If you want to change it to absolute value so it makes more sense to you, it really doesn't matter at all. So this negative is on the outside, which means that we're going to reflect in the x-axis. Now this 3, this is not a reciprocal function because I have something in the denominator. Again, I can rewrite this as negative, and then there's this double thing here. This could be 1/3 times x plus 4, like so, plus 1. Whether or not you understand what the little symbols mean or not, it doesn't matter. That's the function that's happening. And so I'm going to reflect it in the x-axis because it's on the outside. This is happening in here with x, which means that this is going to be a horizontal it's going to be a horizontal stretch, a factor of 3. And then I'm going to translate left 4 and up 1. Number 4, the absolute value parent function is reflected in the x-axis, horizontally stretched by a factor of 3, and translated 5 units right. Write an equation to represent the new function. Okay, so the parent function, f of x, equals the absolute value of x. And so it says we are reflected in the x-axis. So we'll make this g of x since I made the other one f of x. If you didn't even write this, then making this f of x is fine. Reflected in the x-axis, which means the negative is going to be on the outside. Horizontally stretched, that's on the inside. If it's stretched by a factor of 3, this will be 1/3. And then translated 5 units right. So 5 units right means it's x minus 5. And then that's it. But what I have here is not 100% correct because this factor here is always the horizontal stretch or compression factor is always factored out of this. There are parentheses here and they are very important. If I don't have them there, then I'd have to have 1/3 x minus 5/3. But this is the way it needs to be, and that is my answer. Okay, number 5. Greatest integer, which I did not say change this to signum. A lot of you did. I don't know where you got that from. I did not say to change this one. I said you can leave it as greatest integer even though because you're not having to graph it, or you can make it absolute value if you want to. If that makes you feel better, it's fine. Even though this is absolute value too because it's all about the transformations here. So the parent function is vertically compressed by a factor of 1/4, then translated 1 unit left and 7 units up. Write the equation for the new function. So again, I'll make this. Well, this was f of x, and so I'll just use that same one, and we'll make this g of x for this one. So it is vertically compressed by a factor of 1/4, so that means that is 1/4, and it's on the outside. Translated 1 unit left and 7 units up, so this is x plus 1, and then plus 7. Number 6 says transformations were applied to the square root parent function such that it creates an endpoint of 3/8, and if the domain of the function is given by -∞ to 3, write an equation that could represent this new function. All right, so my parent function looks like this. Right? It's telling me that the new function has an endpoint of 3/8. So 3, we made that 3, and this 8. That works. Okay, just sort of making that up right there. And then, so there's my endpoint. And if the domain is from -∞ to 3, that means my square root function goes like this, or it could come like this. I'm not sure. And this does say that could represent this new function, so it's not it for sure, but that works right there. So I'm supposed to write the equation that could represent that. So what's happening here is we've had a reflection. right? The reflection would be across the y-axis. And then a translation, we went to the right 3 and up 8. So this means I would have f of x is equal to, this is the square root, since I'm reflecting in the y-axis, that means it would be inside of here with the x. And then I'm going to move to the right 3, so it's going to be x minus 3. But again, these parentheses here are important because this reflection and the horizontal compression and stretch factors are factored out. So this right here, this negative 3 tells me when I go to the right, and then I go up 8. So it says could because, again, it could have been reflected in the x and the y, so it could come down here. So it could be the negative version of this too. It doesn't matter either way. All right, so then it says a certain function is vertically compressed by a factor of 1/2, horizontally stretched by a factor of 2, and translated left 6. If the new function is represented by this, then write an equation that could represent the original function. So it's the original function to get here. So basically we have to undo it. So if this is, let's see, it says it was vertically compressed by a factor of 1/2, means I need to take this and I need to vertically stretch it by a factor of 2, which means that would give me like g of x is equal to 6 right here. And then it says horizontally stretched by a factor of 2. So if I do that, then that means that I would have to take this one and multiply it by 1/2 to get here. So I need to divide it by 1/2, which is the same as multiplying by 2. So I need to open my parentheses. I'm going to multiply by 2. And then this x plus 7 has to be in parentheses here, or it might not be 7. Then it says, so this is my horizontally stretched, and then translated left 6. So left 6 actually means that we would be adding 6. So we have to do the opposite to this, which would be subtract 6. So this would be plus 1. Close all that, and then minus 4. So then we can check ourselves. And so if I take this, I have to do all of these things to it, and it should give me this. So I'm going to vertically compress it by a factor of 1/2. Multiply this by 1/2, I get 3. Horizontally stretched by a factor of 2, which means that it gets multiplied by 1/2. If I take this and multiply it by 1/2, I get 1, which is basically this. And then translated left 6, which would mean I would add 6. So if I take that 1 and add 6, I get the 7, and then we're good. Okay. So next one says, using the description of the transformations from the parent function, write the function, graph the function, and state its domain and range. Okay, so we have a quadratic function. It's reflected in the x-axis and vertically stretched by a factor of 3, translated left 4 and up 6. So if my f of x is equal to x squared, because it's quadratic, then g of x is equal to, see, it's reflected in the x-axis, so the negative is on the outside, and vertically stretched by a factor of 3, so that's negative 3. Translated left 4, so this is going to be x plus 4 squared, and up 6 be plus 6. That's what my function looks like. Okay, so my domain, my range, we can graph it first or second, it doesn't matter. We have my anchor points are 0, 0 is one of them. So I can start at 0, 0. I'm going to reflect it in the x-axis, which means I don't go anywhere. Vertically stretched, I don't go anywhere. Translated left 4, 1, 2, 3, 4, and up 6, 1, 2, 3, 4, 5, 6. So I'm right here. Then 1, 1 is one of my anchor points. I'm going to reflect it in the x-axis, so it ends up here. Vertically stretched by a factor of 3, so I end up here. Go to left 4, 1, 2, 3, 4, up 6, 1, 2, 3, 4, 5, 6. There's symmetry, so there's my other point. Then 2, 4 is a point. I'm going to reflect it in the x-axis, so it ends up down here. Okay, and then I'm going to vertically stretch it by a factor of 3, which is going to get me at 2, negative 12. but then I'm going to end up going back up 6, so I really end up at -6, which is right here, and then I'm going to go left 4. 1, 2, 3, 4. And then I have symmetry, so it ends up over here as well. So my graph then looks like this. Oh, that was not good. Let me start from here. Okay. So my domain, -infinity to infinity. My range, -infinity to 1, 2, 3, 4, 5, 6. And I include my 6. I never include my infinities. Okay, square root function is vertically stretched by a factor of 5, horizontally stretched by a factor of 2, then translated left 2 and down 8. So my f of x is the square root of x. G of x equals, so it's vertically stretched by a factor of 5, so the 5's on the outside, square root, horizontally stretched by a factor of 2, which means it's multiplied by 1/2 in here, translated left 2, so this is x plus 2, and then down 8, b minus 8. Okay, so my anchor points, at 0, 0 is an anchor point, have a vertical stretch by a factor of 5, go nowhere, horizontally stretched by a factor of 2, go nowhere. Then I go left 2 and down 8. I'm right here. So then 1, 1 is another anchor point. Vertically stretched by a factor of 5. Then I am horizontally stretched by a factor of 2. Then I go to the left 2 and down 8. 1, 2, 3, 4, 5, 6, 7, 8. Next anchor point would be 4, 2. Vertically stretched by a factor of 5, so I end up here at 10. Horizontally stretched by a factor of 2, so I end up over here at 8. I go left 2 and then down 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. And then this looks like this right here. So my domain, going from -2 to infinity, I include my -2. My range goes from -8 to, oh, that's not an 8, goodness. -8 to infinity. And I include that -8. I never include my infinities. Okay, more characteristics of functions and graphs. So use the graph to determine if the relations given below are symmetric to the x-axis, y-axis, or origin, and then we have to confirm our answers algebraically. Well, looks to me like number 10 is going to be symmetric with respect to the x-axis. If that is true, then I should be able to substitute in a negative y and get the same thing back out. So if I substitute in a negative y squared minus x equals 4, that means y squared minus x equals 4, and these two are the same. I have confirmed it algebraically, and I can say it's symmetric with respect to the x-axis. All right, so then number 11. I've got, it looks like it is symmetric with respect to the y-axis, so if I substitute in a negative x, then I should get the same thing. So y equals negative absolute value of 4/3 times negative x plus 5. And so this gives me y equals negative absolute value of -1 times 4/3 x plus 5. So if I just take the absolute, whatever this is, positive or negative, this negative is going to take the absolute value of it, makes it positive. So we really just end up with y equals negative absolute value of 4/3 x plus 5. This is the same thing. So this is symmetric with respect to the y-axis. Then the next one. So this, not symmetric to the x or the y, looks like it has point symmetry, so it's symmetric with respect to the origin, which means I should substitute in a negative y and a negative x and see what I get. Okay. So when I do this, it's still this negative y. It's equal to 2 times the cube root of, so this is like, again, negative 1 times 3x. Well, I can't take the cube root of 3 and get anything, a whole number or anything. I can't take the cube root of x and get a whole number, but this cube root of negative 1 is negative 1. So I can take that out and get negative y equals negative 2 times the cube root of 3x, which means that y equals 2 times the cube root of 3x. And so since these two match, this is symmetric with respect to the origin. Okay. All right, so then I'm going to determine algebraically if it is even, odd, or neither. If even or odd, describe the symmetry. So this goes along with this, but this is actually a little bit easier. So, because instead of substituting in a negative x or substituting in a negative y or both, for even or odd, I find f of negative x every time, and then I see what happens. So if I find f of negative x, this is going to equal 3 over 2 times negative x squared minus 9. So this gives me f of negative x equals 3 over, well, negative x squared is x squared, so this is 2x squared minus 9. And this is f of x, so since f of negative x equals f of x, this is even, which means it is symmetric with respect to the y-axis. Okay, so like all of this stuff is your answer. This backs up what you're saying, and then you've got to say that f of negative x equals f of x, and then it tells you, then you have to say if it's even or odd and what it means about the symmetry. So on here, 14, I find f of negative x. That's equal to the cube root of 3/5 times negative x. So just like on this one up here, this is f of negative x equals cube root of negative 1 times 3/5 times x, which means I can take that negative 1 out. So f of negative x equals negative cube root of 3/5 x. So this is just the negative version of this, which means that f of negative x equals negative f of x. That tells you that the function is odd and that it is symmetric with respect to the origin. Okay, so I'm going to determine if the functions below are continuous. If discontinuous, identify the type and location of discontinuity. All right, so this clearly not continuous because I'd have to pick up my pencil and I'd have to jump to get to the next part. So this is discontinuous. And the type of discontinuity is jump discontinuity. And that occurs at x equals 2. Your locations are always x equals. So here, this one is continuous. Here, this is discontinuous because I have to come up here. Even though I have to like jump to get here, that's not what's happening because I have an asymptote here. And so this is discontinuous. And this is called infinite discontinuity, anytime you have an asymptote. And that occurs at x equals 3. Okay. Then on 18, it's discontinuous because I'd have to pick up my pencil. And this is a hole. So your hole is either point or removable. Those are the same things. just different ways to say it. And that happens at x equals -1. So notice all of my discontinuities, their locations are x equals. Doesn't matter if it's, at a point, you don't put the ordered pair, the location is at x. All right, so we're going to do operations and compositions of functions. G minus h of x. So this is the same thing as g of x minus h of x. So g of x is equal to 3x squared minus 2x minus 5 minus h of x, which is 2x minus 1. This has to be in parentheses because you're subtracting the whole thing. So then this gives me 3x squared minus 4x, and because negative 2x minus 2x, and then minus a negative 1 is plus 1, so that'd be minus 4. And that equals g minus h of x. Even though it doesn't say it here, we still have to talk about domain. So the domain here is all real numbers. This is part of my answer. All right, so then f divided by h of x is the same thing as f of x divided by h of x. So that's equal to f of x is 4x squared minus 1 over x plus 1. So since I already have a fraction, dividing by h of x is the same thing as multiplying by its reciprocal. So I can multiply by 1 over 2x minus 1. And then when I do that, I can actually factor this numerator. So when I multiply this by 1, I'm going to leave the denominator as x plus 1 times 2x minus 1. And then at the numerator, this becomes 2x plus 1, 2x minus 1. And so here, these cancel out. Now when we are graphing our rationals, that means I have a hole there. Okay, and we'll come back and worry about that here in just a second. And then I'm left with this here then, f over h of x is equal to 2x plus 1 over x plus 1. And then I have to talk about my domain. So in this case here, once I get to this point, x is a set of all x's such that x cannot equal -1. Okay. All right. And I need this piece and this piece. F times g of x would be the same as f of x times g of x. So f of x is 4x squared minus 1 over x plus 1 times g of x, which is 3x squared minus 2x minus 5. All that has got to be in parentheses. So I would go ahead and factor the numerator and I'm going to multiply at the same time. So I'm going to factor just the second part because the first part is going to give me 2x plus 1, 2x minus 1, and I know that it's not going to cancel out with this. So I will leave this as 4x squared minus 1, but I got to check the other part of this. And when I factor the second part there, it's going to give me 3x minus 5 times x plus 1 all over x plus 1. And then this will cancel out. And then since it was in my original one, I still can't have the denominator equal to -1, so I got to keep that in mind with my domain. I'm left with these two things here. I'm going to multiply those back together, and then my f times g of x is going to equal to 12x cubed minus 20x squared minus 3x plus 5. And then got this. My domain, though, although it might look like it's all real numbers, it's not. It's a set of all x's such that x cannot equal -1. Because if it couldn't in the beginning, it can't now. All right, 22. F plus h of x is the same as f of x plus h of x. So f of x is 4x squared minus 1 over x plus 1 plus h of x, which is 2x minus 1. In order for me to add these two things together, I have to get a common denominator, so I have to think about that as over 1, and then I'd have to multiply this times x plus 1 over x plus 1, so I can get a common denominator there. It's going to have to happen with this term. So then here, this is going to give me 4x squared minus 1 plus 2x minus 1 times x plus 1 all over x plus 1. Now, I do not get to cancel these out because, first of all, I just put it in there. Plus, there's this big addition sign here, and this isn't all multiplication in the numerator. I need to multiply these two together, so this is going to give me 4x squared minus 1 plus, this will give me 2x squared, and then minus x plus 2x will give me plus x, and then minus 1 all over x plus 1. F plus h of x in the end then is going to be equal to 6x squared plus x minus 2 all over x plus 1. And then my domain is going to be the set of all x's such that x cannot equal negative 1. All right, so then h of g of x can also be written as this. So I have to take the g of x, which is 3x squared minus 2x minus 5, substitute it in everywhere I see an x and h of x. So this is going to be 2 times 3x squared minus 2x minus 5 plus 1. This gives me 6x squared minus 4x minus 10 plus 1. No, it's not plus 1. Take it, it's minus 1, sorry. All right, my board's, there we go. This is supposed to be negative 1, I'm making stuff up there. This is minus 1, minus 1. So then I get h of g of x is equal to 6x squared minus 4x minus 11. And my domain is all real numbers for this one. All right, so f of g of x, I'm sorry, f of h of x. So f of h of x is going to be, take h of x, which is 2x minus 1, substitute it in everywhere I see an x for f of x. So it's going to give me 4 times 2x minus 1 squared minus 1 over 2x minus 1 plus 1. So that means that equals 4 times, and when I square this out, this is going to give me 4x squared minus 4x plus 1, minus 1, over, and then that 2x minus 1 plus 1 is just 2x. When I distribute in the numerator, I'm going to get 16x squared minus 16x plus 4 minus 1 all over 2x. So then f of h of x equals 16x squared minus 16x plus 3 all over 2x. Okay, so let's talk domain. This is the one that was a little tricky to understand the wording. Clearly we can see here that x cannot equal 0, but sometimes it's not that easy to see. And what the deal is that the domain, when you have compositions of functions, is the domain of the second part. So it's the domain of h. So h of x is 2x minus 1. So the domain and the range are both all real numbers. So it's the domain of h of x such that the range of h of x lives in the domain of f. Okay, so let's talk about the domain of f of x. Here's f of x. X cannot equal negative 1. All right? So that means h of x cannot equal negative 1. So if I think about that way, the h of x cannot equal negative 1 because of this domain right here. So if I write that down and I say, all right, h of x cannot equal negative 1 because you can't equal, x can't equal negative 1 for f. And basically this becomes my x's. That means that h of x, which is 2x minus 1, cannot equal negative 1. When I add 1 to both sides, that means 2x cannot equal 0, so x cannot equal 0. And we can see that that's what's happening here. Because in the end, for this one, I could just take the domain of this piece. But sometimes things cancel out and things change and you have additional pieces. So you got to make sure that you can look at that analytically like that. But what's happening here then is what this tells me and what I can get from here is that the domain is a set of all x's such that x cannot equal 0. Okay, so now we're going to use these here to evaluate each function. Okay, so we're not really doing compositions of them here. H plus g of negative 2 is the same thing as h of negative 2 plus g of negative 2. So h of negative 2 is going to be the absolute value of 3 times negative 2 plus 9. Plus g of negative 2 would be 5 times negative 2 squared minus 3. So then I just got to clean all this up. Absolute value of negative 6 plus 9 plus this negative 2 squared is 4 times 5 is 20 minus 3. So this is the absolute value. This would be 3 plus 20 minus 3 is going to be 20. And that is h plus g of negative 2. All right, so g plus f of 4y minus 3 is going to be g of 4y minus 3 plus f of 4y minus 3. So g of 4y minus 3 is going to be 5 times 4y minus 3 squared minus 3. Plus f of 4y minus 3 is going to give me 2 times 4y minus 3 plus 7. This gives me 5 times, this will be 16y squared, and that would be minus 12x, so minus 24y plus 9 minus 3 plus 8y minus 6 plus 7. So I'm going to distribute this here. This has to be distributed, so this is going to give me 5 times 16 is 80. So I get 80y squared minus 5 times 24 is 120y. 5 times 9 is 45. And then this negative 3 and this negative 6 can give, and this positive 7. So this right here will be 1 and then minus 2 plus 8y. So clean all that up together and I get 80y squared minus 112y plus 43 is equal to g plus f of 4y minus 3. Okay, then f of g of 3p is f of g of 3p. So I think I will find g of 3p first. So this will give me 5 times 3p squared minus 3. It's going to be 5 times 9p squared minus 3. which equals 45 p squared minus 3. So I'm going to take that, substitute that in here for f. So this will give me 2 times 45 p squared minus 3 plus 7. This gives me 90 p squared minus 6 plus 7. So f of g of 3p equals 90 p squared plus 1. All right, inverse functions. It says determine if the graph represents a one-to-one function. One-to-one function means that it's going to pass the horizontal and the vertical line test. And so passes the horizontal line or the vertical line test, passes the horizontal line test. The answer is yes. 29 fails both of them. Fails the vertical line test, fails the horizontal line test, so that's definitely a no. It's not one or the other. 30 passes the vertical line test, also passes the horizontal line test, so the answer is yes. All right, so then 31, I'm going to find the inverse of each function, then graph both the function and its inverse. All right, so let me find, actually I'll just start by graphing this one, and then I will graph the next one. So f of x, this is a square root function. My anchor points, 0, 0 is one of them. But this is not factored out. I have to fix this. So this has to be the square root of negative, and then this would be x minus 6. That always has to be completely factored out to see all of my transformations. All right, so I'm here at 0, 0. I'm going to reflect in the y-axis. That's what that does, but that doesn't do anything right here. And then I move to the right 6. 1, 2, 3, 4, 5, 6. All right, so then 1, 1 is an anchor point. I'm going to reflect in the y-axis and then move to the right 6. 1, 2, 3, 4, 5, 6. Then I can be at 3, 4, 2. I reflect in the y-axis and then I move to the right 6. So I'm right there. Okay, so my function looks like, oh, sort of missed. That's a little bit better. So there's that. So then I have to find my inverse. So the inverse, if I think of this as y, I exchange my x and y, this is going to become x equals the square root of negative y plus 6. And whether I use this one or this one, it doesn't really matter because I just have to do the work in the end. So I'm going to square both sides. I'm going to get x squared equals negative y plus 6. So then x squared minus 6, oh, that is an x. X squared minus 6 equals negative y. So then I multiply through by a negative 1. I'm going to get negative x squared plus 6 equals y, which means f inverse of x is equal to negative x squared plus 6. Had I used this one, I would have gotten the exact same thing. But we need to talk about domain here. So let's go back to our original function. So for this function here, for my purple function, my f of x, my domain is negative infinity to 1, 2, 3, 4, 5, 6, to 6. So negative infinity to 6. My range goes from 0 to infinity. Oh, but I include my 0. Oh, I include my 6 also. Goodness. Okay, let me do this. So I include my 6 here. Back that up. And then my range is 0 to infinity, and I do include my 0. Now, when you find the inverse and you exchange x and y, you also exchange the domain and the range. So the domain for f prime of x is the range for f of x. So my domain here is 0 to infinity. This is important because this, as it is a quadratic. It's going to be a parabola. But that's the inverse of this does not give me a parabola, it only gives me half of it. And here's how I know which half. Okay, so let's graph that half. My anchor point for my quadratic, 0, 0, works. This negative is affecting the y, so it's going to be a reflection in the x. So at 0, 0, I don't go anywhere, but then I go up 1, 2, 3, 4, 5, 6. So then when I'm at 1, 1, I'm going to reflect it in the x-axis, and I end up here, and then I go up 1, 2, 3, 4, 5, 6. When x is 2, I'm at 1, 2, 3, 4. That's my anchor point. I reflect in the x-axis, so I end up down here, and then I go up 6, and end up right there. And then this is my inverse, okay? And remember, the inverses are reflections in the line y equals x, and so that's what it should look like. They should look like reflections of each other when you're done. All right, so 32. This is an inverse function, and I can write this as -3 times 1 over x plus 4 to kind of help me with my transformations. So I will go and graph this one. When I do this, I do not have a vertical shift here, which means that my asymptote stays at y equals 0. And then I do move to the left 4, so 1, 2, 3, 4, so does my asymptote. So my original function here, if I start at 1, 1, and I have a reflection, and this will make this a reflection in the x-axis, a vertical stretch by a factor of 3, and then I move to the left, 1, 2, 3, 4. Okay, so my graph basically looks, oh, goodness, basically looks something like, oh, pretend like I hit that. And then -1, -1 is another anchor point. I reflect in the x-axis, vertical stretch by a factor of 3, and move 1, 2, 3, 4. Okay, and then it looks something like that. Okay, so there's my original. Then I have to find the inverse. So when I go to find the inverse here, make that y. So I switch those to get x equals -3 over y plus 4. So I would multiply both sides by this y plus 4, so I get x times y plus 4 equals -3. I'm trying to get y by itself, so now I'm going to divide by x, so I get y plus 4 equals -3 over x. Then I'm going to subtract 4, so y equals -3 over x minus 4. So f prime of x equals -3 over x minus 4. Okay, so there's this. For my original one, okay, this one right here, my domain, so my x's, I'm going from -infinity to -4, and then from -4 to infinity, so go from -infinity to -4, and then -4 to infinity. My range goes from -infinity to 0, and then 0 to infinity. So remember that the domain and range switch places here. So this domain is going to be -infinity to 0 and 0 to infinity. So I know that before I ever start. Then I'm going to figure out my asymptotes from here. I do have a vertical shift here going down 4, so my asymptotes is at y equals 0 goes down 1, 2, 3, 4, goes to here. There's going to be a lot going on this graph. This one, I just have here, it stayed here. Okay. And then when I graph the rest of this, my anchor point at 1, 1, This gives me a reflection in either axis. We'll go with x. So I'm going to reflect in x. I have a vertical stretch by a factor of 3. And then I am moving down 4. 1, 2, 3, 4. End up right there. Looks something like this. And then I have -1, -1 is an anchor point. I'm going to reflect in the x-axis, vertical stretch by a factor of 3. And then move down 1, 2, 3, 4. I didn't mean to make a point there. It's going to look something like this. And then you can see, again, a lot going on in this graph. But I do have, if I draw in my line y equals x, right here, then I can see that that is actually a reflection. A whole lot easier to see that with a bunch of different colors. You do it all in pencil, which it's okay if you did, but it's just going to look like a hot mess of stuff. You might not really be able to see the reflection in that line as well. All right, piecewise functions. It says graph the piecewise function, identify the domain range, and state the location and type of any discontinuities. All right, so in order to graph these, I know that this is going to graph as a line, but I don't get the whole line only when x is less than or equal to -3. So I need to figure out what's happening at -3. If I take this -3 and I substitute it in here, then this is going to give me -1/2 times -3 plus 3. So that's going to give me +3/2 plus 3. So that's 6/2, so that's 9/2. Basically will be my y value. So when x is -3, 1, 2, 3, I'm going to go to 9/2, which is 1, 2, 3, 4.5. And it's a solid circle because of this right here. Then from this point, this is a line, so my slope is a -1/2. I'm going to rise 1, run to the 2 left, or 1 to the left 2. Then rise 1 to the left 2. So then when I draw that in, looks like this. Bam. Okay. So then I need to figure this out. This is a quadratic, right? The quadratic's going to have 2 open circles on it. And so I got to figure out where those are. I'm going to substitute in that -3 first. So get -3 squared minus 1. I'm also going to substitute in that 1. So -3 squared is 9 minus 1 equals 8. And then 1 minus 1 is 0. So when x is -3, y is at 8. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. And it's an open circle. When x is 1, y is 0. And it's an open circle. Okay, but I don't get to just connect the dots here. This is a parabola, so I still have to think about my transformations and what's happening here. I use my anchor points, all that good kind of stuff, but I just don't get the entire thing. So if I was going to graph this right here, 0, 0 is an anchor point. The only thing that's happening there is a vertical translation down 1, so that 0, 0 just comes to here. Okay, that's my vertex, so it's going to come down and back up. -1, 1 is an anchor point, but my transformation, I go down 1. -2, 1, 2, 3, 4 is an anchor point, but I go down 1. So now there are my pieces there that I can, and that's the piece of the parabola that I have. Then I have this, which is a horizontal line. So y equals 3 when x is greater than 1. So this is also an open circle. When x is 1, y is 3, and it's an open circle. When x is 2, y is 3. When x is 4, y is, it's a horizontal line. That's what my pieces look like. So then my domain. Okay, so I go from -∞ to, all right, I'm here at -3, but although the function is discontinuous, my domain is not discontinuous here. And then I keep going. I got all these x values, but here at x equals 1, I don't have an x value. So that means I'm going from -∞ to 1, and then from 1 to infinity. My range starts here at -1. I include the -1 because that's a closed circle. So even though this is open, I do have a y value there. I keep going, this is open, but I have a y value. Keep going, this is open, but I have a y value. So it's going to infinity. And then, is my graph discontinuous? Yes, it's discontinuous in two different places. Here, this is jump. So I have jump discontinuity at x equals -3. And then I also have jump discontinuity and removable at x equals 1. So it jumps and I have a hole missing. So it's jump and removable at x equals 1. So my graphs of polynomial functions says, given the graph of the polynomial functions below, determine the sign of the leading coefficient and whether the function has an even or odd degree. So I've got, it's up, up, which means it's going to be even. And since it's up, up, and not down, down, then it's going to be a positive leading coefficient. And then these are opposite, which means it's going to be odd degree. And if it's odd, then your cubic, which looks like this, is which will be your positive. So it would be down, up, but this is up, down, which means it has a negative leading coefficient. And that concludes part 1.